So, in the last class we looked at the concept of engineering stress and engineering strain. So, the engineering stress is given as sigma equal to P by A naught, where P is the load applied and A naught is the for a uniaxial tension test. In the context of uniaxial tension test we were discussing, and A naught was the original cross sectional area, right. And then we have defined sigma T equal to P by AI, whereas AI is the instantaneous cross sectional area, right. This is original and this is, these two things are going to be different as you continue the deformation, and that is the reason why the values that you would obtain for an engineering stress and a true stress will be different from each other. And then your strain is defined as, let us say, final length minus initial length divided by initial length. That is the definition of your strain, right? Change in length to the original length. And we have defined d epsilon T is equal to dl over L, and if you want to find out epsilon T, that means if you integrate it from 0 to whatever strain that you are interested in, then this will be epsilon T, that will be equal to integral initial length final length dl over L, that is natural log LF by L, right. That is the definition of your true strain. All right. Now, if I were to, so epsilon can be written as LF by L naught minus 1, or 1 plus epsilon is equal to LF by L naught, right. So, that implies I can write my true strain is equal to natural log 1 plus epsilon, because this quantity is basically this, and that is how your true strain and engineering strain are related. All right. Now, let us try to relate the true stress and engineering stress. So, we know that true stress equal to P by AI. So, if I multiply this guy with A naught and divide this with A naught, then I have P by A naught times A naught by AI. Okay. So, P by A naught is what? That is our engineering stress. I am not writing anything as a subscript to sigma when it is an engineering quantity. If it is a true quantity, then I am writing subscript T. Okay, that is how you recognize, times A naught by AI. And now we have discussed about the volume constancy condition, which means A naught L naught must be equal to AI Li. Okay, is that acceptable? So, that implies A naught divided by AI will be equal to Li by L naught. Let us say this AI Li that we are talking about is LF, that means the final length, right. So, then I can write this guy here, sigma T equal to sigma times Li by L naught or LF by L naught, the instantaneous one, wherever you want to find out. So, what do I know about LF by L naught? Again, I know that LF by L naught is 1 plus. So, that is how you can relate the true stress with the engineering stress and engineering strain, right. So, given your true quantities, you should be able to find out engineering quantities and vice versa. All right. So, if you would draw now the true stress strain curve, normally you would have drawn, you would have obtained out of your experiment typically the engineering stress strain curve that looks something like this. The blue color one is the engineering stress strain curve. But if you would draw the true stress strain curve, when you are drawing true stress strain curve, your area should be instantaneous area, and the instantaneous area when you are doing the tension test, AI is going to be larger than A naught or smaller than A naught? AI is going to be smaller, small, because you are increasing the length, so cross sectional area has to reduce. So naturally your sigma by AI, P by AI will be having a higher value than P by A naught. That is why that curve is up. You can see that the red one is your true stress strain curve. For the time being, forget about this dashed line. That is something called Bridgman correction. We will talk about it in a moment, but for time being, don't think about it. You are only going to focus on the blue, solid blue line and solid red line. So the solid red line is your true stress strain curve. Okay, and we have all just now shown the relations between true stress and true engineering stress strain and true strain and engineering strain. Okay, so in the when we have looked at our stress strain curve, we have looked at this peak, right? That is what we call ultimate strength point. So the stress corresponding to that peak in the engineering stress strain curve is what is called ultimate strength of the material. Okay, so now that is where in a ductile material, that is typically what is observed in a ductile material, the localized deformation takes place. That means typically in a ductile material, this phenomena called necking happens. So the local cross section suddenly starts decreasing. This means all the deformation is localizing in that area. That is why it is called localized deformation. And eventually failure happens there. And that is the mechanism responsible for this necking is in ductile materials is actually void coalescence, and voids will coalesce with each other, and as a result you will have net local reduction in volume. We have assumed volume constancy, right, until now. But then the moment your necking starts, the volume constancy condition cannot hold good, because microstructurally what is happening is you have a material, let us say, and you have voids are present in this ductile material. These voids are coalescing with each other, and as a result the total volume of the material is getting changed. So the volume constancy condition cannot hold good in the necking region. Okay, so during necking all the deformation is localized. So you cannot, if you think about the defining, for instance, true strain as a function of length, it becomes a little tricky because the deformation is localized, and hence instead of writing your strain in terms of length, you might want to write just before the onset of necking, you might want to write in terms of area, cross sectional area. Okay, so you can use this. We have defined the relation between AI just before the onset of necking. This is not during necking, just before the onset of necking. Epsilon T will be ln A naught by A, right? And then you can write that as a function of D naught, assuming your specimen to be cylindrical. Okay, this expression is only true for a cylindrical specimen. If it is some other specimen, then D naught by D does not work out, right? Because you have to write appropriate cross sectional area formula. Okay, so the true strain in this case should be usually is calculated using local cross sectional area variation, ln A naught by A. So you will be, if it is a cylindrical specimen, you will be measuring the diameter changes during this process. All right. So typically what happens is, you have just now seen that your true stress strain curve, if you see the corresponding point for ultimate strength point on engineering stress strain curve is M, on the true stress strain curve it is M dash, and typically the true stress strain curve will always be left to engineering stress strain. Okay, and then the flow curve beyond this point, it is many times it is found to be linear in this region. okay, but sometimes it need not be, but many times it is found to be linear. So for some materials it may be non-linear too, okay. And now if you look at the stress at the ultimate point, that means the where the necking is happening, that is the maximum load carrying capacity of the material, right. It cannot hold any stress beyond that value. After that, actual failure is happening. So that is why it is called ultimate strength of the material, okay. So the ultimate stress sigma u is P max by AU. So AU is the area corresponding to the onset of necking, and then you can write epsilon u, that is true quantity, is ln A naught by AU, that means corresponding to the onset of necking, that means the peak point. So you can write again sigma u in terms of P max and then connect that with epsilon u and see sigma max times e to the power epsilon. That is something that another relation, particularly in the position where we are talking about the onset of necking. All right. Many materials. So we have the, so far when we have done the uniaxial tension test, when we have looked at uniaxial tension test in the last class and this class, we have identified the initial elastic regime. That could be a linear elastic regime or a non-linear elastic regime. If it is a linear elastic regime, then the slope of the line in that linear elastic regime is called your elastic modulus, right. Slope of the stress strain curve is what we call as elastic modulus or Young's modulus of elasticity. If it is non-linear, this slope is not going to be constant, and hence you need to take something called tangent modulus, that means local slope. And that is what we have learned about the elastic regime. And then this elastic regime is followed by a phenomena called yielding, that means the onset of plastic deformation. That is when the dislocations in the material start moving. Until then they are not activated, right. So that means your stress is not large enough to actually cause the dislocation. So at the onset of yielding, so that is why yield point represents the onset of plastic deformation. Until yield point you will not have plastic deformation, okay. So that is again the property of the material, right. Depending upon the kind of material that you are using, your yield strength will change. Similarly, your elastic modulus will change from material to material. That is why these are material properties. And then if you load the material beyond the yield point, you continue the plastic deformation, but the thing that you will observe is the material becomes hardened. That means it becomes harder and harder for you to cause further deformation, right. And this regime is called hardening regime. From the yield point up to the necking is called hardening regime. And beyond necking, so once the necking represents the onset of localized deformation, right. And then usually after necking, if you are looking at engineering stress strain curve, your stress strain curve falls down because the force required to cause further deformation will go down. Previously, until ultimate point, the additional force required to cause further deformation was increasing, right. But after necking, the force required to cause further deformation goes down. That is the reason why your engineering stress strain curve goes down, right, because your P divided by A, in the engineering stress strain curve, the area is original cross sectional area, which does not change, but P does change. The fact that P is reducing, that is the reason why beyond necking the stress strain curve drops. But if you take true stress strain curve, why is it not dropping? It is continue to grow. That is because your cross sectional area is actually reducing, right, significantly as you continue the load, and hence although your requirement for P is also increasing, A is reducing, the total quantity is increasing, right. So that continues to go up. All right. So now we have defined the first region, which is called linear elastic regime. So we have a formula for that, that is represented by Hooke's law, right. Robert Hooke, it is named after Robert Hooke, is the English engineer or a physicist who I understood the elastic deformation of the materials, who did seminal experiments in understanding the mechanical behavior of the material, right. So, sigma equal to E times epsilon is the formula that we use to represent the linear elastic part of the system. And then how do we go about representing the hardening part? That means from the yield point to the necking, what is the functional form that we use, right. So, there are several functional forms that are available. So, usually the power law true stress strain curve, power law is one of the popular models, wherein if you are plotting on the y axis, it should have been sigma t, because true stress strain and true stress and true strain. Okay. Then if you plot on a logarithmic scale, you will have a straight line, or in normal scale it will be looking something like this. And please note that this power law is from the yield point, not in the linear elastic regime. In the linear elastic regime, it is anyway, it is E times epsilon. Okay. So, there are two constants to represent the behavior of the curve. So, this, if it is a linear n equal to 1, then it is called linear hardening. So, you will have a material, this is your linear elastic regime. So, let us say this is your yield strength sigma y. From here onwards, the behavior, you can have no hardening at all. When n equal to 0, then sigma t equal to k, some constant, that is basically your sigma y, and this is what is called elastic, this is elastic, perfectly plastic material. There is no hardening at all. The material continues to deform at constant stress. That means, if you were to see that from the microstructural mechanism perspective, there was no resistance to dislocation motion whatsoever. So, and hence you are able to, at the constant stress, you are able to have deformation. That means you are able to impart strain to the material, right. This is an idealization. Typically, there are no materials which can actually show such a behavior, but it is an idealization. This is what is called elastic perfectly plastic material. So, several times when you want to test the behavior of the materials in the plastic regime, when you are writing your own numerical codes, the simplest possible thing is to do this. So, you study what is the behavior of the system when the material is elastic perfectly plastic, because you do not have to worry about hardening, right, because you do not know much about the hardening behavior. So, and hence you try what happens if at all it is perfectly plastic, which is an ideal case. And then when n equal to 1, then this can be something like that, and this is what is called linear hardening, and you can also have non-linear hardening, something like that. Okay. So, depending upon the value of the exponent, you will have different responses. When n equal to 0, it is perfectly plastic, n equal to 1, it is linearly hardening material, n equal to half, then it is non-linearly hardening material. Okay. All right. So, this power law is only valid in the uniform plastic deformation regime. So, until the onset of necking, there was no localization. The plastic deformation was uniform everywhere within the specimen. But the moment necking starts, the localization kicks in. That means you cannot call that situation as uniform plastic deformation. All your plastic deformation is happening at one place. Everything else is sitting, doing nothing, right? So, this power law formulation is only applicable until, as long as your material undergoes uniform plastic deformation. Okay? This n is what is called strain hardening exponent. It is a material property again, right? Depending upon the kind of the material, whether you have a linear hardening or non-linear hardening and so on. So, this n is what is called strain hardening exponent. Okay? And we have given one form, that sigma t is equal to k times epsilon t power n, right. But there is nothing special about this form. There is, in principle, you can write different kinds of forms that you want. Okay, people can come with different kinds of forms as long as they match with the experimental results. So that is why I am saying there can be several other forms of power law, and there is nothing fundamental about the expression. So you don't have to have so much of attachment to this power law, the way that we have written. There are other forms. For instance, this is another form which will say that it will include your plastic strain. You have written in terms of plastic strain, because until elastic regime it is plastic strain is 0. So you have taken that into account, and then you have written that without actually worrying about where you are starting this. And there is another expression which is an exponential form written this. So all these forms are possible, and also some of these forms. So people come up with different forms. Why do they have to come up with different forms of this expression? Because somebody has given power law and they have done this experiment, their experiment for the particular material, and this set of materials doesn't seem to follow the power law. Then they have looked at it, okay, the power law is not working. So this is not a power law material, but it is some other material. Okay. So material is behaving the way that it wants. It is just us who are associating some mathematical form to it. So, and hence we should not attach too much of value to the particular mathematical form that we are attaching to this behavior. And no matter what mathematical form that you attach, it may actually match very well with the experimental results, but that does not mean that it can actually explain all the mechanisms, microscopic mechanisms at play in the material. You are just hypothesizing the macroscopic behavior of the material through a mathematical form, but that in no way can represent all the microscopic mechanisms, because it's all, after all, this is a law describing the macroscopic phenomena, where you don't have any information about the microscopic deformation mechanism, right? And hence we should be very much careful when we are looking at these stress strain relations in the plastic regime, particularly because there can be several other forms one can fit in, and that form can work for a particular class of materials. The same form cannot possibly work for other class of materials. Okay, so you please keep that thing in your mind. And the reason why sometimes it may work and sometimes it may not work is because primarily the plastic deformation is a path dependent process. Okay, that's a very important thing to remember. So because when you are writing your, for instance, if you are modeling plastic deformation in a material, it is extremely important that you actually carefully follow the path dependency. Otherwise, you will be actually estimating your stress state in a completely wrong manner than what it is supposed to be. Okay. And of course, we have discussed that there are different microscopic mechanisms that can be operating at different regions of the stress strain. So you possibly cannot use one law to describe every part of the stress strain. All right. So as we have discussed, there are many models which are developed to incorporate the microstructural mechanisms through some constants like the K and N. These constants sort of represent the microscopic mechanism in some average sense, but they cannot represent the microscopic mechanism at each and every point on the stress strain curve, because the mechanisms themselves might change when you go from one region to other region. For instance, some physical processes like creep, fatigue and environmental degradation such as corrosion are much more complicated to be explained through simple laws that we have discussed, right? So it's simply not possible. So if you want to incorporate new mechanisms, you probably have to deal with more and more complex models to describe the mechanism. Okay, and as we have discussed, it is not going to take into account the true stress strain curve does not consider the triaxial stress state that exists in the necking region. So it does not worry about it. The true stress strain curve does not take into account of this triaxial stress state that is existing in the necking region. and as a result, that means there is local hydrostatic stress that is present during neck increasing, and that is not usually taken into consideration when you have drawn the true stress strain curve, but which has to be considered. So Bridgman did some experiments and he suggested that you need to take into consideration of the existence of the local hydrostatic stress, state of stress during necking. We will talk about it when we are going to discuss failure theories, why one should be concerned about local hydrostatic stress in this situation. So he suggested, and hence the true stress strain curve, the way that it is drawn, the solid red line, is not entirely true. You need to account for some correction which has been suggested by Bridgman, and hence the dashed line came in. That is the true stress strain curve. Yeah. All right. So this is the corrected. The dashed one is the corrected stress strain curve. All right. So I think I wanted to also discuss with you another concept before going on to. Okay, let me finish this condition for onset of necking, right? So when you are drawing engineering stress strain curve, so that is your ultimate tensile strength. So that is the onset of necking, right? This is the process during which necking evolves, but the onset happens here. Necking is not progressing here, it is just started. It is like this point where plastic deformation started, it did not progress. Similarly, necking started, did not progress. This is where the necking is progressing. Okay. Now you can actually write from the load perspective, you can write this as dP equal to 0, right? The variation, that's a peak point, right? So you can write P equal to sigma T times A. Is that acceptable? Yeah, that's what we have learned. So I can write the variation of P as sigma T dA plus d sigma dA must be equal to 0, right? And now I will leave you here, and now if our hardening response is represented by sigma T is equal to K epsilon T power n, what is the condition for necking? What happens at the onset of necking to d sigma T by d epsilon? Can you go about deriving that? So you start here and you know everything about the stress strain relations, right? So now I want you to find out this guy. So you know that at the onset of necking this is the condition. So you can clearly see that d sigma T by d epsilon T is equal to K n epsilon T for n minus 1, right? But at the onset of necking, what happens to this? This must be equal to something that should come from this. Can you find a relation between sigma T, d sigma, so what is, so normally you say that if d sigma by d epsilon must be equal to 0 at the onset of necking, right? So similarly d sigma T by d epsilon T, that is actually equivalent to this case, right? This condition is same. So now you have a variation in area. So you can write from the volume constancy dA by A in terms of dL by L, and from there you can bring in the true stress strain value, right? And hence you would be able to correlate d sigma T by d epsilon. You can get d sigma T by d epsilon T from here. What should that be equal to? And then equate that to this guy. So you have to get what is d sigma T by d epsilon T from this relation, right? And that equate that to this guy, and then you will say something coming up. So at the necking, d sigma T by d epsilon T is not equal to 0, right? it is not equal to 0. d sigma t by d epsilon t is not equal to 0 because there is no peak in true stress strain curve. d sigma by d epsilon is equal to 0 or dp equal to 0. Okay, so this is what I have written, right? So dp equal to 0 from volume constancy dl by l equal to minus dA by A, that is d epsilon t, and then you can write d sigma t by d epsilon t is sigma t, right, which means this is sigma t. So the variation of true stress, the necking begins when the variation of true stress with respect to true strain becomes equal to true stress. That is when necking begins. That means, again, if you want to further work on it, epsilon t power n divided by epsilon t is equal to sigma t means k times epsilon t power n. K gets cancelled, epsilon t gets cancelled. Therefore, epsilon t equal to n. In other words, when your true strain becomes equal to n, the hardening exponent, that is when necking begins, right? So in the case when you are writing from the perspective of true quantities, the necking begins when the strain rate of change of stress in true quantities becomes equal to true stress. That is the key. d sigma t over d epsilon t becomes equal to epsilon. That is nothing but this. When your true strain, that is E epsilon t u at the onset of necking, that is u I have written because it is ultimate point, right? That must be equal to n. That is when necking begins. Right? Oh yeah, sorry, sigma t. I have said sigma, but I have written epsilon. Thanks. Yeah. All right. So you can actually say that when n is equal to epsilon t u is the ultimate strength at the ultimate point, because that is where we are saying the necking begins. Okay. So this criterion for necking is called considerous criterion. So consider has given this criterion in terms of true quantities. It's the name of a person. It is not consideration. All right. Because in the engineering, from the engineering strength also, the necking begins at the peak, right? So that is equivalent to the variation of from the engineering stress strength of d sigma e by d epsilon e equal to 0. Yes. All right. Before I move on, I would like to spend a couple of minutes on giving a little bit more understanding. Okay, let us say you have this stress strain curve. For time being, let us draw engineering stress strain curve. All right. Okay. Now I am doing this test, and this is my sigma y. Now let us say I have loaded this guy up to here, and then I decided to unload. What happens? I have loaded up to this point. Now I decided to unload. I will come back along. Okay. So I will be able to come back here. So what is the amount of plastic strain at this point? 0. There is no plastic deformation, and hence it should be 0. Now let us say I have loaded up to this point. Okay. Now I have not gone to the region of necking. I have only loaded up to this point. And now if I unload, what will happen? What will be the path? Parallel to straight line, parallel to true. This region, this line. Okay. What did you say? Hooke's region. Okay. So you will unload along a line whose slope is equal to your elastic line. Why is that? Why should it be parallel to that line? No, you said you have to unload like that, right? These two should be parallel. Why should it be parallel to that guy? Why should it only unload along that line? Because when you are unloading, you are not causing plastic deformation. Your plastic deformation is over. All the unloading is only elastic, right? So elastic behavior is described by elastic stiffness. So that is the reason why it has to only go along that path. It cannot choose any other path. So this is your unloading path. Very good. So now when you have loaded the guy up to here, your total strain, you please pay attention here, it is very important concept. This is your total strain. So let us say 0, A, B and let us say C. And now I have unloaded to zero stress. Unloaded means I have no to zero stress. I could actually go in the opposite direction, but I am not talking about it. Zero stress. Then what happens? Because of the fact that I have gone into plastic regime, I am not able to get to this point where I have actually started, right? So what happens here? So what is the amount of strain that I have recovered? This is the total strain, but this much strain is recovered, right? And this much strain is retained. So what should I call this guy and what should I call this guy? Which one is plastic? First one or second one? So this is your plastic strain, this is your elastic strain. So your total strain is given by elastic strain plus plastic strain. Is that clear? So now I have unloaded, I had my tea and then come back. Now if I start to reload the machine, system, take the sample which is unloaded up to here. Now I am doing the experiment again. How will it start loading now? Along the same line, okay, and it will go up to, what will be the yield strength of this material? Will it be this or that? What happened to the material? You have got the same material, right? Huh? Did you change the material? It was the same specimen, but now if you do this experiment, you are observing that the material has a different yield strength. How is this possible? So the most important point to realize is that when we are moving along each and every point on that line, you are actually transforming your material. It is not the same material anymore. It may have same elastic modulus, but it definitely does not have same elastic modulus. Its yield strength has changed. You have actually changed the material for good by doing plastic deformation. That is why we say by doing plastic deformation, you are hardening the material, right? So if you are given a material which is loaded to plastic regime and unloaded, and if you are given that specimen, and if you are trying to find out the yield strength of the material, you will find that to be more than what it would have been for a virgin material. So by plastic deformation, you can harden the material or strengthen the material. So if you take that specimen, is it going to be more brittle compared to the virgin material or not? You will find that this is getting more and more brittle because it is actually going towards its failure point, right? So that is, so the important thing to realize is that when you are doing this plastic deformation to a material, from each and every point you are actually transforming your material. You are not the same material anymore, okay? And then you do further load it here and unload it here again. So let us say this is your peak, then again your yield strength is going to increase, right? It again increases, unload and reload, then your yield strength is increased. And if you have loaded just below before the necking, and then you will see that suddenly the material is failing without giving you any sign, right? So a ductile material, which is a material which is ductile to begin with, could actually be hardened significantly just by plastic deformation. Yeah. So that's a very important thing to realize when you are looking at mechanical deformation of materials. Okay. So with that I will stop, and in tomorrow's class we will discuss about the remaining mechanical properties, measurement of remaining mechanical properties.